then you know that there's a forward and a reverse reaction. So what you want to look at is first look at the first two and the last two, and you're trying to figure out, okay, which ones look the most similar. So if you were taking this first one, NaHCO3, what do you think it looks the most like on the product side? Which one? The first product or the second? It looks more like the second one. Do you see the CO3? Okay. So the only part that's the same with the first one is the sodium. So the rest of them change. So can you see that this, the CO3s and the CO3, so they're the most similar. And then this, H3PO4, is similar to NaHPO4. So then in the next question, so what happens to the hydrogens for the first one? Does it gain or does it lose hydrogens? Going from NaHCO3 to H2CO3, it gains. It goes from NaHCO3 to NaHCO3 to H2CO3, so it gains. It gains a hydrogen, so that makes it a acid or a base? It makes it a base. That means that H2CO3 is the it's the conjugate acid, right? So remember that the base on the left will form the conjugate acid on the right. So now if you look at H3PO4 and look at its sort of partner on the opposite side, do you see that it goes from H3PO4 to NaHPO4? So that is what? What happens to it? It goes from 3 hydrogens to just 2 hydrogens, so it loses. So it loses hydrogen. And so that makes it the acid. And so that means that NaHPO4, NaH2PO4 on the product side, that is the, yes, the conjugate base. So remember, the acid always forms the conjugate base. The base always forms the conjugate acid. So now I have all of this in a container. What will happen if this is at equilibrium? You tell me which direction will this reaction shift if I add NaHPO4. Will it shift forward or reverse? And I don't care if you think forward or reverse or right or left. Which one? Whichever one. It's going to go in reverse. Okay? Because if I add, whatever I add, the reaction shifts away. So I'm adding product. And that is going to cause the reaction to shift away from the product side, which would mean towards the reactant side. What if I add H3PO4? Which direction? It'll be the forward reaction then, because if I add H3PO4, see that it's a reactant? So here I'm adding a reactant. So that'll cause the reaction to shift away from the reactant side, which causes it to shift towards the product side. Now, what if I remove energy? What if I cool this? So if I take this system and I decrease the temperature, which way will the reaction shift? To the right or the left? We'll go to the left. Anytime you remove, the reaction shifts towards what I remove. So if I remove reactant, because do you see that energy is a reactant? Energy is on the reactant side. If I remove reactant, then the reaction will always shift towards whatever I remove. So it's going to go to the left. And then if I remove H2CO3, find H2CO3, which way will the reaction shift? Forward or reverse? Forward. So the reaction will shift forward because I remove product. So the reaction shifts towards the product side. So just remember, if you add reactant, the reaction shifts away from adding that reactant, so it'll shift to the right. If I add product, the reaction shifts to the left. If I remove reactant, the reaction shifts towards whatever I removed. And if I remove product, the reaction would shift the opposite direction, shifting towards that removed product. So remember, all the goal is to try and make it back to equilibrium. So if you add something that upsets equilibrium, and it just shifts to try and reset or restore equilibrium in each case. So these ones would be like good ones to practice, like these ones. You can go, you can download like the blank PowerPoint ones. So that way you can kind of go back and just practice picking those ones out. Which are the acids, which are the base, which are the conjugate acids and conjugate bases. But then also in addition, like think about them from this point of view, where I went through the example of looking at a reaction that's at equilibrium and how the reaction shifts when you change criteria or reactant or product content in a reaction. Try to make up another one or two of those. Okay, so where we quit last time is we were talking about the pH scale. So I told you that you have the scale goes from 0 to 100. Remember that they have, when you look at this table, it makes it look like the pH scale starts at -1. It doesn't. The pH scale actually starts at 0. Concentrated hydrochloric acid is not naturally found, which is why its pH is more concentrated than the pH scale, because you don't normally find it. So when they developed the scale, it was based on known things. Anything that's above 7 is basic. The further you go towards 14, the stronger the base. The more hydroxide ions. So remember that that's going to have more hydroxide ions. Remember those corrosive reactive ions. The closer you get to 7, like so pH of 9, 8 going to 7, those are called mild bases because they don't make a lot of hydroxide ions. Exactly at 7, that's neutral. And now when you go below 7 and you're in the acid range, pHs of below 7, but going really all the way down into pHs of 4, those are called mild acids because they don't create a lot of hydrogen ions. But remember, those strong acids have lots of hydrogen ions, lemon juice, stomach acid, vinegar. And so those can cause corrosion. Those can cause breakdown in tissues on those extreme scales. Now, interestingly, and one we're going to talk about is here's blood. The pH of the blood is actually slightly basic. It's between 7.35 to 7.45. So that is the normal pH, physiological pH. And for 99.9% of people, their blood pH never changes beyond this. But if you look at a scale of 0 to 14, that's pretty narrow. 7.35 to 7.45 is a pretty narrow range that the pH can exist in. And that becomes important when you start looking at different health conditions. So we're going to talk about buffers in a minute. But here's how to calculate. So everybody grab a calculator when they came in. Anybody need a calculator still? So doing these calculations, this is really the only math. So the big important thing to do, oh, you grabbed one. You got yours? Okay. So the important thing to do is make sure that you put it in your calculator right. Okay. So for example, this one, this is given a 0.050 molar hydrochloric acid solution, HCl. So that is a concentration because it's that capital M. Remember, that means moles per liter. So this is the concentration of the acid. Now, HCl is the concentration of a strong acid. Hydrochloric acid is a strong acid. And remember, you know then that 100% of the molecules form ions. So therefore, the concentration of the acid is equal to the concentration of the hydrogen ion concentration. So they're exactly the same. Because they're strong, because HCl splits 100% into ions, the concentration of the acid is equal to the concentration of the hydrogen ions. So in doing this calculation, if you want to figure out the pH, You can do it from the old calculator or the new calculator. So if you're using one of my calculators, it's the old calculators. Old calculators, you have to put in a number and then you do the function. You can't put in the function first. So in this one, you actually have to put in the concentration of the acid. So in this one, you would put in 0.050, the concentration. Then you hit the log button. And then you hit the little plus minus button. See, there's the button that looks like that. The one down near the equal sign. If you have a new calculator, so Amber, like yours, you actually put in a new calculator, you hit your plus minus button, then you hit log, and then you would put in the concentration of 0.05. And what'd you get? Did everybody get 1.3? Anybody not? Okay. So that's the steps. If you have the old calculator, you kind of look like you're doing it backwards. Concentration, log, then plus minus. If you have a new calculator, that allows you to put the functions in before you put in any kind of number. Now, if we want to go the other direction, so if we want to know how much the acid concentration is from the pH, we can just do it as by kind of like reversing the process. So in this, if we want to know the acid concentration, so we'll just put H3O plus, it is going to equal the inverse log of the negative pH. So if you look on your, if you're doing, so we can say if the, say the pH is 4.67, then you want to find out what is the acid concentration. With the old calculator, you have to put 4.67 in. You have to hit the plus minus button. Then you hit the second log, which is that 10 to the x. So in the old calculator, you have to put in the negative pH, then the second button, and then the log button. So I will put in 4.67, hit the little plus minus button down next to the equal sign, and then the second button, then the log button. And I get 0.00002138. If you have a new calculator, you just put it in straight. So in the new calculator, you put this, you hit your second button, then the log button, and then put a plus minus sign, and then 4.67 and equals. If it gives it to you in, so 4.67 negative second log. If I want it in scientific, it would come out looking like 2.13796,209 times 10 to the minus fifth. And there's a way you can actually flip back and forth with these. Do you see where numbers 4, 5, and 6 are? See numbers 4, 5, and 6? See the green numbers above? So if you want to put it in English, that's flow. I don't know why it's not ENG. But if you want to put it in English, you hit second and number 4. If you want to put it in scientific notation, you hit second and the number 5. Can you do that? Make sure that you can, so put that down like, so if you see a number and you may have to round, like for example, this one, I need 3 significant figures in my number. Well, my long number is fine because it's 2138, so I could just use it. But if it wasn't, and I only had like 1 significant figure and I needed 3, then you have to put it in scientific notation. All you have to do, put a note, it's the second button and number 5 is what puts it into scientific notation. Second button and flow, F-L-O, which is number 4, that puts it back in the expanded form like regular writing. So you see that in this one, so I've got In my number, I have 3 significant figures. So when I come to this, the 2, 1, 3 are my first 3 significant figures. The next number's an 8. So that's going to cause it to round up. So it would be 2.14 times 10 to the minus 5th. And that's actually a concentration. It would be that capital M for molar. It would be fine if you put 0.0000214 M. Either one would be fine. They mean the same. So just add that as a note. If you have the old calculator, second flow, put your number in regular format. Second 5, put your number in scientific notation. So you can flip back and forth that way. You don't have to clear it. You can just, it's just changing how it's displayed. So let's do a couple ones. So in this one, what is the pH of a 2.65 times 10 to the minus 5th molar HCl solution? So to do this one, you've got to remember how to put this in your calculator. How do you put 2.65 times 10 to the minus 5th in the calculator? What do you have to use? That EE button. So put this, so you'd put 2.65, then you hit the EE button once, and then put in the 5, and then that little plus minus symbol. If you're using the old calculator, you put in the concentration, then hit the log button, then make your number positive. If you're using a graphing calculator, you hit the plus minus button, then log, and then put in the concentration. And you'll notice when you get your answer, it ends up being a really big number. So pH equals minus the log of 2.65 times 10 to the minus 5th molar, 4.576754126. Everybody get that?
You said for the old calculator to put it in.
First, put in the concentration.
Yeah.
Then hit the log button. Then the plus minus button. So did you put in 4.65 EE5 minus for concentration? So clear? Because I didn't see you push those numbers. 4.65, or sorry, 2.65. 2.65 EE 5, and then the plus minus. Yes, that is that number. See that exponent up there? That is 2.65 times 10 to the minus 5th.
Okay.
Now you hit log, and that plus minus button, and it just turns it positive. So you see that? Okay. So in the graphing, the big thing, 1, you got to make sure you put your exponents in right, and then 2, make sure you do it in the right order. So how many significant figures in this answer? There should be 3, right? Because 2.65 has 3 significant figures. So the 4.57, next number is a 6, so what does it do? Rounds up, so it's 4.58. So now if you're going the opposite direction and you know the pH and you want to figure out the concentration, if you have the old calculator, you put in the number for pH, make it negative, and then hit the second button and the log button. So you put 1.68, make it negative, and then hit second and log. And you got one of these. If it came out in scientific notation, your number would be 2.0892696,131 times 10 to the minus 2. If it was in normal expanded form, then it might look like 0.020892961. So you should have one of those. And you can actually flip. If you hit second and flow or second and psi, you can actually flip from one to the other. Did everybody get that? Can you see it? Not that one? Okay. Make it negative. Now second and log. Okay? So do it in this order. So put in the pH, hit the plus minus, then second and log. So inverse means the second button. 3 significant figures in 1.68, so I'm going to have to round that one as well. So this one, 2.08, or I'd go all the way to the 0.0208. Next number's a 9, so that would round up or down. Up, just going to round it up. So I'd end up with 2.09 times 10 to the minus 2, or 0.0209. And it's molar. So that capital M is at the back. Those are the exact same. One's in scientific notation, the other one's just in normal form. So I want you to, we've got that one, yeah, we'll do these two, and then I'll let you do the last one for homework, and then we'll practice it again next time. So this one, what is the pH of a sample of sodium hydroxide with a hydrogen ion concentration of 1.45 times 10 to the minus 12? And that should be capital M, should be molar. And then, is this a strong acid or base, a weak acid or base, or is it neutral? Okay, so what did you do with this one? What's the steps? Put the 1.45, then the EE button, and then the minus 12, and then you hit? Second log. Not second log, so if you're finding pH, it's just log. And then the plus minus button. Okay, so you put in the exponent. If you're using the old calculator, do the exponent. So 1.45 EE, 12, make it negative. Then you hit log and make it positive. So the number you got, I got 11.838632. Did you get that?
Is it supposed to have a negative?
Well, but see, you make it negative at the end. You make it like it comes out negative, you make it a positive. So you just hit the plus minus button at the end to change the sign. So did you get 11.838632?
Well, I got 1.18. So is that
Okay. So put 1.45, 1.45 EE12 negative. Log, I got 11.8. Did you put to the negative 11? 1.45, then EE, and then 12 and make it negative. And make it negative. It's got to be the negative 12. Now get log. Oh, but it's to the 1. It's to the 1. Put it back into flow so that you won't get that wrong. Right? So remember, flow puts it without. So look, if I have it like this, see that little 1? That would mean times 10 to the 1, so that would be 11.
Okay,
So see that little 0, 1 on yours? Yeah, so just hit second and number 4 and put it back into regular form. So you had it right, you put it in right. I was like, how did you put it in with being off by a factor of 10? Okay, so 3 significant figures with 1, this one would be 11.8. So you tell me, would this be a strong acid, a strong base, or more of a mild acid or a mild base? Or is it neutral? 11.8. It's a strong base. Right? Because remember we said things, really anything that is above an 11 is pretty strong. Things that are in the 8, 9, 10 range are more in the mild base. So here's the second one. Second one is, what is the hydrogen ion concentration of a substance with the pH of 8.35? So first off, 8.35, would that be a strong acid, a mild acid, a strong base, a mild base, or is that neutral? That'd be a mild base. So this is really, and mild is a better, because I always think of electrolytes when I think of weak. So this is more of a mild base because it's closer to 7. So 11 up to 14, that is really considered strong bases. Anything that is like 7.01 up to 11 is more of a mild base. It's really like 10. And then going down the other direction, anything from 6.99, going all the way down to about a pH of 4 is considered a mild acid. And then anything below that, 4 down to 0, this is a strong acid. And this really should be closer to like 10 is like close to where ammonia is. Okay, so if I have an 8.35 to find the hydrogen ion concentration, I have to take the inverse log of the negative pH. So the inverse log, that is the second button, then the log button, and it's going to be a minus 8.35. So remember, when you do this, you have to put the number in first. This is how the new calculators do it. Old calculators put 8.35, make it negative. And then hit the second button and the log button. This one comes out as 0.00000000004. So see, like in this one, you can't see enough decimal places unless you put it in scientific notation. Negative 9. Did you get that? So put 8.35, make it negative, second, and log. And that's that number, 4.4668. Or yours might look like 0.00000004. Hit second button and the number 4, or 5, sorry, second button and the number 5 to put it in scientific notation. So remember, when you round this, you keep those exponent numbers. The only thing that I've got to round is 8.35 is 3 significant figures. So that 4.46, next number is a 6, so that's going to round up. So this will be 4.47 times 10 to the minus 9th molar. So you keep those exponents, you're just rounding that number that's out front. But second 4 is putting it in normal notation. Second 5 puts it in scientific notation on the old calculators. Most of the new calculators automatically go into scientific notation if there's a lot of zeros. Okay, so there's 1, 2, 3 right there. So practice these ones. We will do these ones on Monday just to kind of go back and make sure that everybody's on board and figuring out how to put pH in their calculator. And really a lot of this is just practicing. So the very last part of this chapter is about buffers. So we have this range of the pH in the blood. So I told you it's 7.35 to 7.45. That range is really very strictly controlled. If the pH goes above 7.45, that'll actually cause your nervous system to become hyperstimulated. So that just means your nervous system begins to send nerve impulses where it shouldn't. This can cause you to get really shaky. This can cause you to like tremble. This can actually cause a convulsion. But worst case scenario, this can actually trigger irregular heartbeats. So you can end up with what they call an arrhythmia, which is an irregular heartbeat, and that can actually lead to cardiac arrest. So it doesn't happen if your blood pH goes to 7.46, but that is what can happen as it goes up. They call that alkalosis because it is when you have too much base in the blood. So the blood becomes alkaline. So the term alkaline means basic. On the opposite side of the coin, if your blood pH goes below 7.35, then there's too much acid in the blood, and this has the opposite effect on your nervous system. So your nervous system begins to shut down. So this person seems to be sort of like, well, in both cases, they may seem out of it. They may not seem like quite so coherent, and it's really because the nervous system is having a hard time. But with acidosis, they seem very tired, lethargic. They may actually pass out or lose consciousness. They may seem drunk because they're very unsteady. If if acidosis is not repaired, if you don't do something to counter this, this can actually cause the person to stop breathing. So too much base can cause a heart arrhythmia and lead to cardiac arrest. Too much acid can actually inhibit respirations to the point that you just stop breathing, and you can't go very long without breathing. So both cases, if you have above or below the normal range, it can lead to symptoms that in the worst case scenario can cause death. So, I mean, I know people that have taken care of patients in the hospital that are like, have massive infections, that have uncontrolled diabetes, that have terrible COPD, kind of like close to end stage. So I've heard of blood pHs of being like 6.9. I've heard of blood pHs of being up around 7.8. So they have been more than just a few tenths or hundredths. But that's the challenge. That's why they end up in the hospital, because if you don't do something to counter this, then death is sort of like the outcome. So the number one way that you counter this, any added acid or base, is by buffers. So a buffer is actually a weak acid and its conjugate base, or a weak base and its conjugate acids. Buffers are found in all of your body fluids. So like if you buy like saline for like your contact lenses, it's in a buffered solution so that it's balanced to the concentration, the acid and salt concentration that's normally found in your tears. And that's why you can put your contacts in and they feel normal. They don't feel dry, they don't hurt, they don't burn, because they're buffered or balanced is really what buffers help to do. So what a buffer does, a buffer takes a strong acid and converts it to a mild acid. A strong base converts it to a mild base. So it takes things that have a lot of hydrogens or hydroxide ions and convert them to molecules that have less. So here's like one example. So here, this is the buffer that's found in your blood. It's called the carbonate, the bicarbonate buffer. And it's actually made of carbonic acid, which is an acid, and bicarbonate ion, which is the conjugate base. And notice it's in equilibrium. So both of these molecules are present. If acid gets added, then the bicarbonate ion will react because acids and bases react to neutralize. So if we add acid, like HCl, that will cause the bicarbonate part to react, decreasing the amount of acidity that's present, and the pH doesn't change. If you add base, then the acid part of the buffer kicks in and helps to neutralize it, keeping it from changing. So by having both like an acid and its conjugate pair, conjugate base, by having them both present, they can both react to acid and base that come into play, and they try to maintain this equilibrium, this balance. And the result of that is that the pH doesn't change very much. And I'll tell you that 99.9% of the time, buffers can maintain blood pH. It has to be pretty extreme for other things to have to kick in. So for the majority of people in this room, you're never going to have acidosis or alkalosis. It has to be things like an extreme condition where the buffers can't manage to try and balance out and maintain the equilibrium of having a weak acid in its conjugate base, balancing out any added acid or base that comes along. But it can happen, and does happen, with patients that have COPD. So COPD is called chronic obstructive pulmonary disease. That's what that stands for. So when you think of something that's chronic, what does that mean? It's chronic versus acute. What does chronic mean? Long term, right? So something that's chronic, you have over and over and over. So people have chronic sinus infections. They just keep getting them. Okay, arthritis is a common bone ailment, a chronic one. So chronic just means that this is not something that just happens. I will tell you, like, pneumonia can lead to COPD, having chronic pneumonia, having chronic bronchitis. People that have respiratory infections more than twice a year, you're at high risk of developing COPD. Patients that have asthma, because with asthma, your respiratory tract shrinks. So the tubes that lead to the spaces where you have gas exchange go from being normal size to being very, very small. So it's very difficult to get air in. So if you can't get air in, that means that you don't get good oxygen and carbon dioxide exchange. So what begins to happen if you can't breathe? Carbon dioxide begins to increase. So think about equilibrium. This is at equilibrium. If you can't breathe, carbon dioxide builds up. Which way does this reaction shift? To the right or the left? To the right, right? So then the reaction shifts to the right, which then creates more acid. You've got some conjugate base in the blood to normally balance this, but you've only got so much. So if acid gets pushed, eventually the buffer can get what they say overwhelmed. So the buffer can only neutralize but so much acid. And if that comes into play, then you can end up with acidosis. So they call this respiratory acidosis because it's all because of what's going on with your lungs. So respiratory acidosis is because of lung damage. You can't get rid of CO2. So CO2 builds up, and that ends up creating acid in the blood. So a patient comes in, so a patient with emphysema, which is one of those end stages of COPD. So they come in and their blood pH is too low because it's acidic. One way that they'll try to treat this is they'll give them bicarb. So if they give them bicarb, the bicarbonate ion acts to neutralize. So if you look, do you see that if I add here, which way does this reaction shift now? So it's at equilibrium, and I add bicarb, the reaction now is going to shift back and help to relieve the excess acid. Unfortunately, if you're talking about COPD, this is just, you're just trying to help. You can't fix it. Asthma, you can give them inhalers, you can give them bronchodilators, things to try and get rid of it. COVID, unfortunately, not in everybody, because COVID is sort of a weird virus, but if the person has respiratory complications from COVID, that can cause scar tissue, and that can really lead them to having COPD pretty quickly, all the result of having that COVID infection. So they end up with what they call glass lung, because it literally, when they take an x-ray of their lungs, it looks like broken glass because of the amount of scar tissue that develops. And it's really odd. I know lots of people that have had COVID. Some of them had terrible coughs and colds, but I know people that had no respiratory problems at all. They just felt like they had flu-like symptoms. So they were really achy, ran a fever, had headaches, but had no respiratory complications at all. So, and then I know people that they look like they had a cold and it was no worse. So it really did have some variations in terms of how some of those symptoms came out. But a lot of the patients that didn't survive, it was because of this. It was because severe lung damage compromised the ability of carbon dioxide to diffuse out of their blood. And eventually, the amount of acid, you can't counter it, but so much. You can keep giving them bicarb, but you're not fixing the problem. So that's always the challenge with the COPD patients and those long-term COVID people, is they just don't have good gas exchange anymore. So they have no oxygen, high carbon dioxide levels. They're always in this slight acidotic state. So the other acidosis, and I thought I left it in. The other acidosis, though, you can make too much acid. This happens if you are not filtering it correctly. So metabolic acidosis, so kidney failure. Metabolic acidosis is commonly caused by kidney failure because you're not filtering waste like you should. Liver failure. Can lead to metabolic acidosis. Untreated diabetes. Because there's a lot of those keto acids. Remember we were talking about diabetes? So you can have excess acid production. Those are really probably the three big ones. Patient comes in, if they're in liver failure, kidney failure, or have very poorly managed diabetes, then they may have acidosis. So again, notice the treatment for this is the same. They still treat them with bicarb because there's too much acid in the blood. So we're going to give you bicarb. Bicarb is a base. The acid and the base then help to neutralize one another and shift the pH back into balance. But you've also got to treat the problem. So the patient needs a liver transplant. The patient needs to be on dialysis. The patient needs insulin. So with metabolic, it's because there's something out of whack in the body and you've got to fix it, or else you're just going to have the problem. With respiratory acidosis, there's very little that you can do if you're talking about scarred lungs. You can't fix those. I know that they have been doing lung transplants on some patients, some of the long-term COVID patients that have the glass lung, that they've been actually doing transplants, giving them new sets of lungs, because that's basically the only option. They have no other option that's there. You really don't see the other two. I'll just tell you, if you're in the hospital, you really don't see the other two. Respiratory alkalosis and metabolic alkalosis almost never happen. It's always the acidosis. So, oh, there's another one. This massive infection, what's called sepsis, that's actually when you have an infection in your blood. Sepsis, this can start because of a wound infection that then ends up getting into the bloodstream. This could start off as just inflammation, but then ends up allowing bacteria to migrate or enter into the blood. That's another one that can cause metabolic acidosis. But alkalosis is really pretty rare. Respiratory alkalosis, this happens if you breathe too much. So this can cause, like if you hyperventilate. So if you have like an anxiety attack, I don't know if you've ever seen anybody that's like hyperventilating, you'll notice they're really shaky. That's all because they're breathing too fast. Their carbon dioxide levels drop too low, and that causes their blood pH to shift too high. And so that creates that like hyperstimulation of the nervous system. Same thing, if you've ever been sick and you're like vomiting and you can't stop, kind of, have you ever done that? You're like, why? You're just like, there's nothing in my stomach, but I'm still retching kind of thing. You're shaky then too, right? Afterwards, you're like, you have this sort of crazy, like, kind of sensation. That's all because of alkalosis. But in that metabolic alkalosis, this can happen because of excessive vomiting. And it's really that you lose too much stomach acid. Right? So normally stomach acid mixes with your food and it gets absorbed. So it goes in and it's part of like what normally comes in during digestion. So if you get rid of excess acid, then you can shift and end up with that alkalosis issue. Both of these ones are really like, they try to like restore, make you stop vomiting, stop all of that, and then treat the underlying disease if it's metabolic. If it's respiratory, they do the breathe into a paper bag thing, which is really not the best way to do it. Because if you breathe into a paper bag too long, you can actually go into respiratory acidosis because you re-inhaled too much CO2. So it's really best to try and calm the person down. But I've seen somebody like get so upset like they passed out. And if they pass out, they'll start breathing normal again. Because then your brain just kicks in. So your brain takes over. Because your brain is really like when you're sleeping, it's your brain that triggers respirations. So if your CO2 level is way too low, your brain will just stop breathing for a while and then it'll start back up normal. Last thing to tell you about this. So I said buffers. Buffers are the #1 way that you maintain pH. As long as your buffers are there, present and balanced, 99.9% of people never have an issue. If there's too much acid or base, the buffers try to balance it, but then your lungs can actually alter breathing to increase or decrease the amount of carbon dioxide that you exhale. So if you have acidosis, then you might be breathing carbon dioxide faster trying to get rid of excess acid. If you have too much or not enough carbon dioxide, like what happens in the person that hyperventilates, if they pass out, they'll stop breathing. They'll just stop breathing until carbon dioxide levels build back up. So I always think of the lungs as like the backup. As long as your lungs are functional, if there's too much acid, you can breathe faster. Not enough acid, you'll breathe slower. And then the last one are the ones that do the fine tuning. The fine tuning are your kidneys. Because remember, your kidneys are your filters. So the kidney's job is to filter out waste, excess salt, excess water, but the kidneys can also filter out excess acid or excess base. So it's constantly like monitoring as blood flows through the kidneys. If there's too much acid, then the kidneys will get rid of it so you can excrete it. So they're sort of one, they don't do it quite as fast. This is going to take like 24 hours to make changes. So you don't expect your kidneys to kick in and restore balance straight away. That's why they might have to do something like give you an IV push of bicarb to try and get that blood pH back down or back up to normal. But the kidneys can help. It just takes some time. So that's why I say instead of being like a quick fix, this is more long-term. Your kidneys help to fine-tune the pH to keep it right between 7.35 and 7.45. But if you have a patient and you see that they're giving that patient bicarb, odds are very high that they have too much acid in the blood. So they're giving them bicarbonate in their IV solutions as a way to try and raise their pH to get it in that range of 7.35 to 7.45. Okay, so that finishes that chapter. So it rolls into chapter 10. So chapter 10 is all about proteins. And in fact, really the back end of this chapter we've talked about, because we've talked about enzymes. So we're really not going to spend a whole lot of time talking about them since we've already covered them. But in this, the first part of this chapter is really like, what are proteins and what are they made of? So Mr. Awadallah sent me that cartoon. So the amino acids are the building blocks of proteins. An acid with an attitude is amino acid. Huh. He thought it was really fun. I was like, okay, I'll put it in my PowerPoint. Okay, so proteins, like polysaccharides, they're polymers. So this means that they're just chains. There's many of them. The building blocks are amino acids. There are 20 different amino acids that humans use to build protein. Some proteins are little, like insulin. I want to say insulin is 37 amino acids. I don't know why that number sticks in my head. So some of them are really pretty small, like insulin. It's a really small molecule. Some of them are huge. Remember we were talking about proteins in the blood? I told you about albumin. So albumin's about 300. So some are small, some are large. We're going to talk about the order and how these amino acids affect the structure and then the function of proteins. And then this is sort of like examples of some of the functions that proteins have. But we're actually going to go over the 8 main functions that proteins have in the body. So first off, the whole reason they're called amino acids, amines. So amines contain what? Anybody remember? In the functional groups, you have amines and amides. Both of those have. Do you remember what atom? Amines and amides. They both have nitrogen. Yeah. Mm-hmm. Uh-huh. Yeah. So NH3s and the N with the double bond oxygen. If there's a nitrogen, it was either an amine or an amide. Okay? So amino is because all amino acids have at least one nitrogen. So there's one nitrogen, there's 2 carbons, which is kind of funny. So it's like NCC, like Nash Community College. So there's a nitrogen and there's 2 carbons. The end carbon is like a carboxylic acid. So do you see how on this side, that carboxylic acid is the COOH? Well, this one is lost. It's hydrogen. Typically, your amino acids, the amino side has a positive charge and the acid side has the negative. But those are always exactly the same. So this part that I kind of drew in purple on this part, the NCC, the nitrogen having hydrogens, the second carbon has 2 oxygens, one's a double bond. That's always exactly the same. The part that is different among the 20 amino acids is that part that they call an R group. So this one, it's R because they called it the residue. It has also been described as being the side chain. The R group, this is what differs in the 20 amino acids. The purple part that I drew is exactly the same for all 20. So another interesting thing is that amino acids, all but one of them, have a chiral carbon. So if you look at the center carbon, do you see that the 4 groups are different? So it has a chiral carbon, which is only just 1, so it only makes 1 left and right hand form. Remember that we said like sugars exist as D, like D-glucose is the common sugar. amino acids almost always exist as L. Just sort of an interesting thing that they're different, they're not the same one. So it's just referring to the position of those groups hanging off of that chiral carbon, but L amino acids are the common ones. I saw an amino acid in some kind of drink and they were like, it helps to give you energy. And I was like, I don't really know about that. But it was listed as L-threonine. Ooh, that sounds fancy. And I was like, that's just an amino acid. Why are they saying that that's going to give you energy? I don't know. Like they like to make like, you know, all the health claims. Like this is great for you. This is all you need in your life to be happy. So there's 20 amino acids. That R group is the part that we want to look at because the R group is either going to be nonpolar, which means it's hydrophobic, right? So remember that's hydrophobic. So remember that's not going to mix with water. So if you have an R group hanging off of that center carbon, it's not going to want to mix with water, kind of like those fatty acids. Or it could be polar. So remember polar amino acids, they're going to have some oxygens and nitrogens in them. So those are going to be hydrophilic. It can even be charged. If it's charged, then it's really ionic. The charged ones, they call them acidic or basic. So they're ionic, and they would also have that hydrophilic characteristic. So any amino acid that's polar charged is going to want to mix with water. Any amino acids, though, with those hydrophobic groups are going to want to separate. So here's the first group. These are the 6 nonpolars. Okay, and so I'm going to try and blow it up because remember that this is the fun part. So in this one, so there's glycine. So see that NCC that's kind of in beige? That's exactly the same. So if I look at this one, or if I slide down, see NCC on this one, or if I slide across, see NCC on that one. So notice that that beigey that part, that's the NCC that's all the same. Every single amino acid has that. The part that's different is in purple. So notice like alanine, it has a methyl, a CH3 group. That's nonpolar. Leucine has a 4-carbon group. That's nonpolar. Coming back over here, there's glycine, has just a hydrogen. That's nonpolar. Valine has 3 carbons. Nothing but carbon and hydrogen. That's nonpolar. So any of these being nonpolar, that's going to affect where they're going to be in the protein because they're not going to want to interact with water. So that's going to come into play when we look at sort of the structure of this. So there's isoleucine. Of course, it goes away. So there's isoleucine, and that one has 4 carbons in a chain. One that I wanted to show you is this one. And this one we've actually talked about. And it's not over there. I know that it's not as bright. Well, that's better. I didn't even know I could do that. All right, so if you look at this one, see the purple? That's that aromatic ring. Right? So remember the alternating single and double bonds? This is phenylalanine. This is one of the components that they make, I think it's Splenda, that they make with Splenda. Is it Splenda or is it aspartame? It's one of the artificial sweeteners. But remember when we talked about PKU? Remember when we talked about if you're missing the enzyme to break down phenylalanine? They do the heel stick on every infant before they leave the hospital and test them for PKU. PKU means you don't make the enzyme to break down this amino acid, and it builds up and ends up having neurological effects. So that was why, so one of them, well, I can't make it do it. Just doesn't want to anymore. Just a little longer. But that one's the one that comes into play. Those are the nonpolars. Couple more. So looking at this one, methionine, I thought there was more than 6. There's actually 9. Looking at methionine, notice it's just carbon, but there's the sulfur. This is one of the sulfur-containing amino acids. Then there is tryptophan. Tryptophan's an interesting one Because it's found in Turkey. Sort of an interesting shape to it, and you look at it and go, well, there's a nitrogen in there, but because it's got those true rings, it's still nonpolar. So tryptophan is actually found in high concentration in turkey meat. Tryptophan is also part of this pathway. So in order to make serotonin, you start with tryptophan. So serotonin is what I always call the calm, happy, peaceful neurotransmitter. So people that have low levels of serotonin commonly experience what? Depression. Okay? So Prozac is a serotonin reuptake inhibitor, an SSRI. And so what Prozac does is it keeps serotonin longer in your brain so that it can up the calm, happy, peaceful mood, because it's a major mood neurotransmitter. Well, tryptophan actually can be converted into serotonin. If you look on the far left is tryptophan, on the far right is serotonin. They're not that different in structure. So having turkey has been shown like to make you sleepy. Have you ever heard that? Like after Thanksgiving, people are like, oh, if you eat a lot of turkey, it'll make you sleepy. Well, that's because it can get converted pretty easily into serotonin. And serotonin is that calm, peaceful, sleepy kind of neurotransmitter. So that's sort of the rationale behind why turkey, I think it has to do with you eat like 3,000 calories and then you need to nap so that you can just digest. Okay, because when you're like digesting a huge meal, that takes a lot of energy, and so your muscles don't really want to do anything. That's more my opinion, but just sort of an interesting thing that these neurotransmitters serotonin looks so much like an amino acid, like extremely similar in shape. All right, so 9 are nonpolar. Then we've got 6 that are polar. These are all polar because they've got oxygens, they've got nitrogens, and that is what makes them, that R group, look polar. So if I can blow those ones up, so see that OH on the end? Even this one, tyrosine. So see that OH on the end? If I come across threonine, this is the one that I saw in the drink that was supposed to give you energy. I was like, what? Okay, whatever. But threonine's one, cystine's another one. Here's the other one that has that sulfur. There's only 2 amino acids that have sulfur. So this is the second one. There's methionine and then there's cysteine. They have a thiol. Remember that sulfur if there's a sulfur at all, it's a thiol. Glutamine and asparagine down at the bottom, these ones have an amide. You see the amide on the very end? Oh, God bless you. Ow. See, it just doesn't. Maybe it does this. Kind of. Nope. Asparagine down at the bottom, that has nitrogen and oxygen, so that would be polar. So the kick in these is all you look for. Just look for a nitrogen or an oxygen in their R group. If you have a nitrogen or an oxygen, odds are really strong that it's going to be a polar molecule. Then the last ones. So they're what they call charged. These are very hydrophilic. These are very want to interact with water, and it's because they have a charge on them as well. So we have aspartate, glutamate, histidine, arginine. See if I can get it to zoom in at least for a minute. So you can see that one. See the double bond, two oxygens, which would make it polar. But in addition, I just can't, it won't let me anymore. But in addition, it used to do this all the time and I couldn't make it stop. Nope. 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 Yeah, I can't. But all of these ones have some kind of charge nature to them. Let's see if it'll zoom. So here's a good one. Here's lysine. So you see that nitrogen on the end. So it's not the part that's the beigey, it's this purple section. So if that R group has any kind of charge to it, So like here, there's histidine. So see the nitrogens on that one? One of them's got a charge. Those are very hydrophilic, so they're going to want to interact with water. Let's see if I can take all my stray marks off. So there's nine nonpolar. There are 6 that are polar. And then there's 5 that are charged. That's kind of their breakdown. Out of those 20, you can make, as an adult, you can make 8. Or sorry, 12, my bad. Okay, so adults, they can make 12 of the amino acids. And if you get a chance to go back and look, you'll see there's ones that are marked with a little asterisk. But the other 8, they call them essential amino acids. Essential means they can't make it. You have to have it in your diet. So this is why you have to have protein in your diet. If not, you'll end up being protein deficient. So if you don't eat these 8, then you won't be able to make all the proteins that your body needs. You can get all 8 of these in any kind of animal meat. So this would be chicken, beef, pork, seafood. So that'd be fish, shellfish, even milk, because it comes from an animal. Cheese comes from an animal. Eggs come from an animal, so all those fall into play too. They're all considered complete proteins. And the amount of protein they say you need every day is a piece of meat about the size of your palm. That's all you need every day, and you'll get all the essential amino acids that you need. Most people eat like 5 or 6 palms worth in the course of a day. Have like the great big huge steaks and everything else, but it's really not necessary. It's a little bit overkill. I guess if you're like a bodybuilder, then maybe you would need more protein. But for the average person, that's about all the protein that you need in the course of a day. But then if you're a vegetarian, then you don't eat any animal products, right? So then they don't eat any meat, they don't eat milk, they don't eat cheese. I can't even imagine. They don't eat eggs. But for that, all they have to do is they have to make sure they get a combination of beans and grains. So beans, which are called legumes, so this could be like black beans, kidney beans, the navy beans. It could be peanuts, because actually peanuts are a bean. Those black-eyed peas, not a fan. But those also fall, even though they're called peas, they're a bean. Okay? All of the peas fall into the bean. Those, they actually have 4 of the 8 essential amino acids. Grains like corn, wheat, oats, rye, they have the missing ones. So by eating both beans and rice, or having peanut butter and jelly on bread, you're actually end up getting a complete protein source, because you're getting both beans and some type of grain. So neither of those are complete on their own, but they will be considered a complete protein together. So if you know anybody that's a vegetarian, they don't eat like one thing. They don't eat like the same thing every day. They really eat a big variety. So they'll eat one kind of bean, then another kind of bean, and they'll like shift it up often to make sure that they're never getting a limitation. Just because by eating a completely plant-based diet, you do have to make sure that you get a much greater variety to make sure that you're getting all of those proteins all the time. So yeah, so if you had peanut butter and jelly for lunch when you were a kid, that's actually a complete protein source. So not necessary that you actually have like meat at every meal. Just something that's got a grain as well as a bean is one that's fine as well. And you'll even see like black beans and rice. That is a common staple in a lot of countries, because there's a lot of countries that protein is really expensive. So eating meat every day is not always an option. So a lot of people would have like rice and then put like tofu in it or have the black beans and rice. There's also like the red beans and rice is another one. And so all those sides that you think about for people that couldn't afford actually to have meat in their diet, they were still getting plenty of protein. So we said any of those amino acids with the R group. Oh, I gotta quit there. It's like, what time is it? It's 6:50. I was like going, wow.